for the introduction, and of course, thanks to the organizer for inviting me to give this talk. So it's the last talk for today, and the wine reception is coming, so I hope you take this talk already easy. I want to sell some ideas. So in the end, I will go to toric situation to explain some applications which I like are beautiful and very nice, but maybe going a little bit away from what the conference is intended to go. But the kind of techniques coming in, localization at toward fixed points, Riemann-Roch techniques, and exactly the techniques we saw in the other talks already. So I was thinking it still would fit into this conference. This is about joint work with Lorenzo Maxim, who is here, and with Sylvain Cappell and Julius Shaneson, who started this subject maybe 20, 25 years ago. We finished in the last year almost a book on this, and I will just explain 96 pages in this 1 hour. Very easy to do, for sure not. So I will just fix key ideas and state a few results. So let's just fix the concept. And I think it was readable from the back if you write in this way. So we start with a lattice. And this choke is really terrible, which will be Zn. We start with the polytope P, which is in the corresponding real vector space, which should be a full dimensional lattice polytope. So lattice means the vertices belong to this lattice. And that means you can write a presentation of P. You can write P as something like these are all points in the vector space, such that the pairing with a normal vector to the facets, I will explain, plus some shifting integers is greater or equal 0. So you get such a presentation by inequalities. And here what we take is, let's see, here we take UF is in the dual of this, so this is in the dual lattice, is by my convention a way generator of the invert pointing normal to the facet. So facet means real codimension 1. And depending which book or author you take, some people prefer the outward pointing, I prefer the inward pointing. So you have a one-dimensional way pointing in, and because there's a lattice structure, there's the first lattice points on this, and that is this UF which we pick. And what is important is that these coefficients AF, these are unique integers given by this presentation, and that is why I need this condition full dimensional to have uniqueness of this presentation. And for most of the talk, not for everything, but if you want to relax, for most of the talk I will assume that P is simple. And simple means at each vertex V is the intersection of n facets. So maybe that's to fix the notation of this. And now I would like to come to fix the dictionary between toric geometry and combinatorial sides of lattice polytopes. So what is the dictionary to move? So on one side we have this lattice polytope. In between we would have the language of fans, which I don't really need today, but usually this is how toric things are presented. And the fan language you can translate into geometry. So that would be a toric variety X. That means you have a torus acting on this. And to be toric means it's normal and you have a dense orbit which is just for torus, and the action is extended, and that would be the geometric definition of a toric geometry. So the dictionary now works in the following way. If you have a face of your polytope, that would correspond to a cone sigma E in this fan, And in the torus, it would be corresponds to an orbit. I prefer to take the orbit closure. So let's call this sigma E closure. So this is where you start with. So if you think in terms of dimension, what here is the real dimension, would be here the complex dimension, and would be here the codimension. So let's illustrate this in the important cases. I go to facets, F, and I have this ray generators. So facet means these are the boundaries of your polytope, codimension 1. If I go to the opposite direction here, this is just a one-dimensional ray. That is where the name ray generator comes from. So here it would be a ray, sigma or rho, maybe the rays usually I write in this way. Still I have this ray generator on this. And here it's most important, it would be complex codimension 1. This would be in T invariant divisor, D rho. So the facets gives you divisors on the toric variety. The opposite, if I start with the vertex, that would correspond to a cone which is top dimensional. So this is 0 dimensional, the cone would be top dimensional, and here you would get a torus fixed point. Yeah, it would be again 0 dimensional. These are the fixed points. And finally, the polytope would be called simple, which I already explained there, or maybe sometimes smooth. If you say I prefer to work with manifolds, that would correspond, that one here maybe speaks about simplicial or smooth fans. And if you don't know this here, it would mean that this is a rational homology manifold, or it would be really a smooth toric variety. Yeah, so that is a dictionary. So most of the time I prefer to, or I need to work with simple polytopes, and then the toric variety is a rational homology manifold, so that means for me Poincare duality is available, equivariant even, so I can switch freely between cohomology and homology, for example. Okay, this is just to fix the picture, and what is most important, maybe I write it still just in one line here. What you see is, or what I've witnessed, the polytope gives you a toric variety, but the polytope gives you more, it gives you an ample divisor. So what you get is you get an ample divisor, D, which I call the divisor of this polytope, and that is where you need these coefficients to build. You just take the sum over all faces or facets or torus invariant divisors. Let's say I write it now in the fan lattice. You take these coefficients here given from the inequalities and you take the corresponding zeros. And then the important statement is, this is Cartier and ample. So that means the projective toric varieties you get, they are projective. And the polytope not just gives you the toric variety, but it also gives you the ample divisor. And I want to play with both of them together. Okay, that is the context I want to work. I fix the notation, and now I want to sell, people who know me, not everyone here knows me maybe, I like to draw diagrams. So this board is perfect. If you want to follow my diagrams, leave enough space on the left, something comes later. So let's see. So I want to explain now in this context the T equivalent Hirzebruch-Riemann-Roch. In this specific context, so for now the toric variety and the ample divisor is fixed. I work in this context. So what I want to do? I want to do Hirzebruch-Riemann-Roch. So I start with equivariant coherent sheaves on this toric variety. So let's say I take an F, or later on you would take a class, and I push this forward to a point, and this push forward, and the twisted version. I push it forward, but I have this divisor. This divisor gives me a line bundle, and I push forward the twist with the line bundle, because that will fit with the lattice point counting I want to sell in the end. And where you end up is then, of course, in the equivalent case theory of a point, which you can identify with the group algebra of the character lattice of M. And now you see here, I should introduce some notions which we fix. I said we start with the lattice. Now you see the lattice is the character lattice of T. And because it is an abelian group, finite dimensional representation split off into character eigenspaces, and that is this identification you are doing here. And I'm pushing forward to a point. I think part of the story is we want to see techniques for maps between manifolds or maybe maps between even singular spaces. This Riemann-Roch transformation, all these things I explained, they are really designed for mapping situations. But for the examples I want to go now, the only map is mapping it to a point. That's for this talk today. But they are designed for more. Okay, so let's see what we are doing now here. What you attach to this player, you attach to this the equivalent Euler characteristic. So let's write this as this is just the equivalent Euler characteristic of X taken with the twisted bounded tensor F. And what does it mean? That means you take the usual Euler characteristic of H star of this player, but you have the torus acting on this, so you can decompose this into eigenspaces. Let's do this in the short notion. So don't be afraid, or maybe by my writing you can't even, maybe I should call this chi m. So this is the eigenspace to the character m, and you write this just with the character, and then you see you end up in this group algebra. So the refined picture is that you not just take Euler characteristics, but you take Euler characteristics with respect to eigenspaces. That's the equivalent Euler characteristic you pick up. That is the thing one wants to calculate, but for calculations, maybe case theory sometimes is difficult. You prefer to switch to cohomology. And that is what the Riemann-Roch transformation is doing. Let's do this first on the point, because that is easier. So here you have the equivalent Chern character. That would go to the equivalent cohomology of a point. Unfortunately, in equivalent situations you have to complete. So the equivalent cohomology ring we have already seen is just a symmetric algebra on this lattice. And now I should emphasize, as soon as I switch to cohomology or homology, I only prefer today working with rational coefficients, because I have quotient singularities, and with rational coefficients I still have Poincare duality, and the Chern character also needs rational coefficients. And the thing is, we have to complete, because this means these are graded things, and you are not taking the direct sum, but you are taking the product of them. That is the completion. Completion just means product, and that comes out by technical reasons. What you are doing here is just you map this to the Chern character of this line model on a point. So this is just ECM. If you say CM is the first Chern class of this line model on a point. But now comes the important point. I think this equality was already in the second talk in the morning, but the thing is, this is not canonical. There's a choice coming in, and I, for my talk, use the opposite to the usual choice. So the choice I'm using is, which we call S, for some reason we will see later. If I have a character, I associate to this minus CM, so the Chern class of the dual character. For some reason, there's a sign choice. So up to sign choice, this is nice. So that is what you do on the point space. So what you are doing now here, now you use what is the equivalent Todd transformation, which is designed for singular spaces. And this goes back to Edith Graham and Wolinski-Zhang. But since I'm now it works in general, but today I want to go to cohomology, because we work with homology manifolds. So for this step, I use now that this is a simple polytope. I can go to equivalent cohomology of X with rational coefficients completed. And if you push forward is on this side, you make a similar thing. You have your integration about X. The OD becomes the first Chern character. So that is just e to the equivalent fundamental class of this divisor T. And then you cap this with a Todd class, and then you push forward to a point. So the commutativity of this is the Hirzebruch-Riemann-Roch, or the Hirzebruch-Riemann-Roch theorem in this context. So as I said, everything works. If I would take here equivalent homology, it would work for any singular space, but I prefer for some reasons now to work with cohomology and lead Poincare duality. That is where I need simple then for that step. Okay, that would be the statement of the Hirzebruch-Riemann-Roch. What is now on the other side coming in is the localized. So the power of equivalent geometry you have seen in all 3 talks in the morning, I think. We want to get contribution from fixed points. And now we make a contribution from torus fixed points. It works for any singular toric variety. We don't never that this is simple or something. But the thing is, I come from objects from K-theory, and you already have a localization on K-theory, which is much easier in the toric context than in general. So the easiness is now very specific to the toric context coming in. So what you're doing if you want to go to, so what you are doing now, you make the same, you make the equivalent Euler characteristic of the section of the affine neighborhood. So what we pick now is, let's say we fix now a torus fixed point. What else we need? Of course, this torus fixed point would correspond to cone of top dimension, and it would correspond to a vertex. Yeah, so it would correspond to a vertex Vx in the polytope. That would be a vertex, depending on which language you want to phrase this. And what I take here is now this Ux is the T invariant affine neighborhood. And this is more or less just the toric variety corresponding to this cone. So you have a T invariant affine neighborhood, so no higher cohomology is coming in. I just make this game with the equivalent Euler characteristic. Everything is fine except that this vector space is not finite dimensional. But the eigenspaces for the characters are all finite dimensional. So if I write this sum up, I do not end up in the group algebra. I just get a formal sum a priori. So each eigenspace is finite dimensional with Euler characteristic, or just the dimension now, no higher cohomology. And out of this, one can make a sort of summation map. And I should say all of this goes back to classical work of Brion and Bern. And the thing is, you get some simple things which are called summable. And then you can take the sum of this. And summable means almost that you are allowed to take the sum of a geometric series, not more, or products of this. So you allow just to take the sum of geometric series, but of course then you have to localize. This is not surprising. So you have to localize. So what is the localizing set you allow? You want to take S is generated by 1 minus some character of your 4 M is not 0, because then you see if I invert this 1 over 1 minus, that is the value which the geometric series with these powers gets. And this is just what you want to allow. And the general theory of Brion-Bern allows you that you always end up here. You can take a sum, and this gives you what we call the projection map to this. On K-theoretic level, it's very simple. Of course, to make it explicit, I will show you in the simplicial context again. But this step is general. I don't need for this simplicial. Okay, that would be the K-theoretical localization. Of course, I can do now the same in equivalent cohomology or homology. Here now you apply again the equivalent Todd, but since I'm on the fixed point now, this is just again the equivalent Chern character. So you end up in equivalent cohomology of the torus of a point, completed. You have to localize similarly, as one should expect. So in cohomology, the multiplicative system, you have to localize this by plus or minus the first Chern class of this element, which is non-zero. And if I would do this with homology, everything would work for any toric, even singular. The nice thing is now, if I do this in the case of simple polytopes, where I can everything phrase in terms of cohomology, it becomes almost as one would expect from the smooth context. So in this case, this is just pulling back and dividing out an Euler class. as one would expect in the smooth context. And here, maybe this inclusion, as you should get, is of course just the inclusion of the fixed point. And maybe I give the Euler class is almost what one should expect. So this is something like pulling back, yeah, but you get a multiplicity in. A multiplicity of this cone, and then you take the normal bundle. Product over rows in sigma 1, so these are those which give you the normal bundle, and the corresponding fundamental classes. But this is a sort of orbifold localization. I have finite quotient singularities, and there are some multiplicities from the stabilizers coming in. Yes, this is an orbifold localization, and that is the thing what you can do here in cohomology. So if you put everything together, or what will be important now is, the important thing for projective toric varieties, this localized information at the fixed point sees everything. So that means if I now go to the direct sum of all fixed points, or let's just do the equivalent cohomology, let's write it this way. If I go to the completed equivalent cohomology just of the fixed point, this map is injective. So if I understand localization, everything is fixed. Yeah, that is a nice thing here. And so here you can, of course, now go back or go. This is, of course, a direct sum of the contribution of the fixed points. So if you understand all fixed points contribution, you know what's coming out, in principle at least. And if you really write this on this side, or maybe here also we make it, here we go now, we have to localize, that's the only price we pay. We have to localize everything. But luckily, localization does not lose any information. It simplifies just the situation. And here, of course, what you are doing is just the sum over the fixed points. You take this localized contribution, which we calculated, and of course this factor you can restrict, it's a cohomology class, you can restrict to the fixed points. This gives you just an E of the vertices, and if you fix my notation, S was a map which I have written somewhere here, which makes identification of the symmetric algebra with the equivalent cohomology. And this is localized Riemann-Roch. And in this way, you can phrase Riemann-Roch, and the important lessons which we have seen in all the other talks today already, I think, we can go to the fixed points, and if we catch what we can do there, in principle we know the players. Yeah? Okay. The application I want to give is, of course, and let me see where my time schedule is. It's okay? Or maybe I should make a break and first ask questions up to here. Because we are not in rush. You want to make pictures, please, without
with you.
With me!
Where
should I be here? Yeah.
Okay.
Okay?
I want to make a point at some point.
Okay, so this is up to now is more or less general nonsense on equivalent Hirzebruch-Riemann-Roch, specified to the simplicial toric projective context. Now I want to apply this. The application which comes in the end has to do with integrating over the polytope and see which kind of lattice point information is coming in. And I like to make this joke to write really here the push forwards as integral over x in the case theoretical or cohomological meaning just pushing forward to a point. In a moment we really see integrals from analysis which are used with the same symbol. Please.
You don't divide by any.
Here I should of course localize.
This Euler class is
Here is a localized contribution. So here are already these corrections, denominators inside.
okay.
This is a localized contribution which I just get if I connect them together. And then I multiply with this player because for the lattice point approximation I need to twist by OD. And where I didn't write should be the local contribution where the Euler factor is in this where I didn't write it out.
Division is somehow inside.
Division is inside here, and inside here it means the sum of these maps.
You don't use y. You do not twist with this exterior power of the
You will see what I will do. At the moment, this is for any coherent sheaf or class of a coherent sheaf. Okay, so now I want to say to which things I want to apply. The lesson I want to tell is these kind of Euler-Maclaurin formulas has a long history. And I mentioned Brion-Ware, for example. And we've taken a lot of ideas from them. And what people classically do is, or what people know from Danilov's work is, that the Todd class for toric varieties has to do with lattice points count. And here now we make equivariant lattice points count. And the power of the equivariance means that we can simulate integrals from analysis. But people just do this classically for the Todd class. That means they apply it to the structure sheaf. The lesson what our paper is about and what I want to sell now is we can do this for every coherent sheaf that contains much more information. We have many more natural examples coming from geometry, and that gives a unified perspective to this. And this lesson I want to sell is this Euler-Maclaurin and toric business are a translation of equivariant Hirzebruch-Riemann-Roch. That is the lesson I want to tell to you. So let's see. So before I make this translation, I should now give some examples of coefficients to which I would like to apply this picture. And now maybe what you asked, the parameter is coming. Yeah? Or if people who have been in the talk on Friday, the subject I'm interested in is about characteristic classes of singular spaces. And we already have seen the chi-y genus. So the class I want to pick out is exactly this class fitting with the chi-y genus. And this is what we call, or I introduced this with some co-workers 25 years ago, or 20 years ago. We call it motivic Chern class, but luckily in the toric situation you can make things very explicit. You have not to know anything about. I can directly say you what it is. So I write this now as an example for those who know the general transformation behind this. That would be all theorems, that this is this explicit player. But we can take this as a definition if you have never heard about. So what we take what we call the equivariant motivic Chern class of X. That is a player coming from abstract business, but here you can write it very explicitly. It's just the same definition Hirzebruch has used in the smooth context. And the important point is, here the head means Savinsky differential forms. So you take only the forms on the regular part and just push forward them to the ambient space. And that is a good notion of forms on the singular toric variety. In the very special case I'm later going on, if I go to simplicial, that would also work for any orbifold. Yeah? The thing is, for toric or for orbifolds, we have a very nice description of the wide omega forms on a singular object we want. And our motivic Chern class is just the generating function of this. And if X would be a manifold, that is already what Hirzebruch introduced in his game of the generalized Hirzebruch-Riemann-Roch. But the nice thing is we have the similar thing here. Take this as a definition. Oh, sorry. Of course, the I is missing. I wanted to check if someone still is awake. It works. You get the first one afterwards? Okay, of course. I want to sum over all. And you will see, of course, this is where parameter y is coming in. That has to do with the chi-y genus we have seen in Anatoly's talk. There's a sign convention how you take the y. Here's a sign. I will not use the sign. I want to fit with Hirzebruch's convention. And this is as a definition, but we call it motivic Chern class because from the abstract theory, this has a motivic flavor that you can decompose this into pieces. That would be a theorem here. So that means what is coming out, that works for any toric. So this would be the sum over, let's do it in the language of the polytope. I start with the polytope. So this is the sum over all faces. You get a correction power 1 plus y to the dimension of the face times the class of the canonical boundary of the corresponding orbit closure. So the nice thing in toric geometry, and this is very specific to toric geometry, we can decompose this into the orbits of the group, and the parameter splits off with this simple combinatorial factor 1 plus y to the dimension. This is very specific to toric. But the motivic nature is they are designed to sum over orbits. You can decompose into pieces. This is usually in classical geometry very unusual, but here you can do. That is what we call motivic churn. And if we go to cohomology, so just apply that we call ty star of x. So this is just the Todd class applied to this player. This is what we call the Hirzebruch class, in honor of Hirzebruch. Equivariant, of course, here. And the thing is, or maybe that's why it becomes better visible. If you take now the degree, you see you have one side the, or maybe I make it twisted. I take a twisted chi genus of x with respect to this ample divisor come from the toric. So if you look about what should it be, I want to calculate the push forward of the coherent sheaves. So for the coherent sheaves, I take now the sum with the parameter. That means I just take a collection together. And if you write it with a parameter inside, you get the formulas nicer if you would like to do it step by step. Yeah, so I plug in a series of coherent sheaves. These are the things I would like to plug in. I twist by this line bundle from the toric variety, and I want to calculate the corresponding Euler-Maclaurin. This is almost what Hirzebruch introduced already, but in this slightly more general context. And so by definition of the Riemann-Roch, this is integral. Well, let's say, can you even do this on a k-theoretical level? So it's pushed forward on a k-theoretical level of this line bundle tensor-wise with this motivic churn class. This is the Riemann-Roch. So this is T equivalent Hirzebruch-Riemann-Roch. If you want to, you can take it as a definition. But this motivic decomposition gives you a completely different formula, which has to do with the lattice point. So what you get is the sum over all faces of the polytope, this weighting power to the dimension of the face. And now you get, you see the lattice points. You see the lattice points in the polytope viewed as characters in some cohomology group. And you sum now over all lattice points, or which are in the relative interior of this face, intersected with the lattice. And you get this, this sum.
This is equivariant. Chi-y.
This is equivariant chi, so maybe I should emphasize this. If you would not do it equivariant, if you only would do counting points, this would be always just 1, 1, 1. So you count how many points are in the interior of a face. But the equivariance allows you to see which point is there. You see the character. That's a big advantage. And I should say this negative is coming in because we take the convention, the torus is acting by multiplication on the torus itself. If I go to the characters which are function on the torus, usually you should say a left action is converted to a right action. I introduce an inverse to make it a left action, and this is why we use this minus. It's not needed here because the torus is commutative, but we prefer this convention, and that is it's just a sign choice. That's not the point. Okay, and this is what you can do there. So when did I start? Half past, huh? Fine. Okay, so this is now first explaining what this kind of twisted chi genus equivariant sees. And the important thing is equivariant sees the characters. It sees the lattice points in the polytope and not just how many points are there. That's the advantage of equivariant. Okay, this is one of the players we want to apply, and this is up to now works for general toric. Here I didn't use simple or something. Now, we now know the answer, what is coming out. So that was on the right-hand side, how Hirzebruch-Riemann-Roch calculates in twisting formation. Now I want to go to the left side. What are the local contributions if I localize at fixed points? How are these formulas looking? So that will be the next I want to explain. And now, now I assume we are in a simple polytope. So now I assume simplicial toric because then one can make everything explicit. So there are formulas for any toric, but they are not very nice. You can write it down, but it does not tell you something. But in the simplicial context, you can make now everything very concrete. And so now I explain to you what are the local contributions in the fixed point formula, in this fixed point contribution. And the thing is, of course, because I'm taking now the context of a simple polytope, so that the toric variety is simplicial, the local situation are quotient singularities popping up. So how to fix this notation now? So now we localize. So I fix a torus fixed point, which should correspond to a cone generated by some ways ρi, which should be a top-dimensional cone because I have a fixed point. And what you can do is now, you have this lattice, and they are included in a bigger lattice, which should be generated by some II prime. And this should be dual to what you get to the lattice generated by the UIs sitting inside the dual lattice. So you have these ray generators, but it's not clear if they are bases of your lattice. Yeah? So if you go to the dual, this can be bigger as the dual of the original sink. And that is what happens here. So this is slightly bigger, but this is a finite index. Yeah? And in the smooth case, that would be inequality. Okay, so what is happening now? So in this context now, you calculate locally on this affine neighborhood, which would be the toric variety corresponding to this cone here. So what you're doing now, there you get now the following representation. You get a finer ring covering of tori. So this is the original torus I'm interested in, but this is the torus coming from the slightly bigger character lattice of finite index. So that means you get here a finite group, which I will call G sigma. My G and my sigma is invisible, what is what. So with this letter I try to say this is the G. And the thing is, this is a finite group. The order of this group is really the multiplicity of the orbifold point appearing in the Euler class. And if it would be a smooth, that would be 1, this multiplicity. And now what you can do is, I have to introduce here, I identify this by some, I fix the basis. You can identify this with C star to the n. You have some projection onto some coordinates. And if you do this abstractly, this character I could call A rho I. So this is just a character from this bigger torus. And the toric variety I'm interested in, or maybe that, this open neighborhood you can get now as if you would do this with the bigger torus, divided out by this finite group, this G sigma. So the good thing is, because now I'm in the simplicial context, this has only quotient singularities by an abelian finite group, and that one can use to make this localization more explicit. So what will be now, in this context, this localization I call projection X to this fixed point in localized K-theory. And the coherent sheaf I'm plugging in now is the motivic Chern class, so a series of coherent sheaves with the parameter yn. So I want to calculate what is the localization as an example of this T-equivalent motivic Chern class of the toric variety. And the formula is not so simple, or I will explain. So you get 1 over the order of this group. You can guess in a moment what this means. You sum over these elements in this group, G sigma, and now you get a product from E equals 1 to n, and the contribution you get is a fraction 1 plus y a rho of G times these characters basis I'm choosing over 1 minus a rho I of G character minus im prime. If you have never seen, that looks of course very complicated. So I think I want to explain this simple idea because it's simple if one knows how the mechanism is. So what we are doing, this is an orbifold situation, and these four omega forms I'm interested in, how they behave. Here this is smooth, these are the usual holomorphic forms. I push forward them under the finite quotient and take the invariants, because this is an orbifold, these are the white objects. So what I'm doing is I want to calculate how many sections there are in a finite neighborhood. Instead of calculating downstairs, I calculated upstairs, and I calculate the dimension as a weighted trace sum. So that is where this player is coming from. Yeah? So you calculate the dimension as the sum over the group traces of this element divided over the order. So it's just a Lefschetz calculation, upstairs. And now we have to understand why in the Lefschetz, where are these factors now coming from? Because upstairs is smooth, it means it's a product of one-dimensional situation, everything is smooth, behaves nice in a product. You only have to understand the one-dimensional situation. And now the one-dimensional situation is so easy that I can even give you a proof, because we have not to prove anything. You only have to explain where this formula is coming from. And this is the following easy picture, which I think one should sell. And since I'm good in time, I will sell it. So we are on a one-dimensional way. Huh? But if you do this abstractly, this comes from a basis chi minus m prime or something, and that you do for all of the ways in my notation there. So here that would be chi minus to the m prime, let's say to the power n, or times n. From the motivic decomposition, which I have given you from the global formula, it works similarly for the cone. You don't need a polytope. It works for the cone. And in the one-dimensional case, what we are learning, the vertex should be weighted by exponent 0, so that should get the weight 1. And all others are on the face, they should get the weighting 1 plus y. So here you put everywhere 1 plus y as a weight. And now you have in addition a finite group acting on this, and you're taking the character of this group element on these one-dimensional spaces. So what comes up in the end is, here you get nothing, here you get in character AG, here you get in character AG to the power n, because you are on the n tensor product of this one-dimensional representation. And you have to take the sum of these players. And then you see what you get if you sum up. What you get. If you sum up, you get this 1, and you get the geometric, and 1 in front of the geometric series, everywhere you have this weighting factor 1 plus y. And now you have just to move the geometric series 1 starting at 1 and not at 0. So that means this is A, G, chi minus m prime over 1 minus A, G, chi minus m prime. This is just a geometric series. And if you put this onto one fraction, you get the expression we have. Chi minus m prime, 1 plus y, a g, chi minus m prime. This is exactly how these factors are looking. That's all. So this explains these local factors. So it's a Lefschetz calculation, linear algebra. If you know the big machinery of sheaf language and toric geometry, it's very easy. That is what you should see. So the local contributions we know now. In the simple case, I'm only speaking now, from now on. And the local case uniquely fixes the global, because the map to localization is injective. Nevertheless, for the application we have in mind, and the application Brion-Wern had also in mind, we need a global version. We need the global counterpart of this formula. And that one has to guess in some way. Either you are clever and understood what Brion-Wern has done, or instead what we have done, what I will not explain today, instead of this simple exercise at fixed points, we have done the global machinery for a GIT quotient, representing the simple toric as a GIT quotient, and using deep theorems of a Lefschetz-Riemann-Roch designed for this situation to produce another proof. And from this one can really see how the formula should look like. But once you know how the formula looks, I will present it, you can prove by this simple exercise and the localization that this is the right answer, if you know how the formula should look like. So here's now the global answer, global for this simple toric context. So what is the answer? The Hirzebruch class, I now go to cohomology of this toric variety, is still what you do, a correction factor 1 to n minus r. R is the number of ways, sigma 1, so this is the number of ways, n was the dimension. You get a sum over a big group of the Fane, which is the union of these G sigma which are introduced. And now you take almost such an expression we have. If you do it correctly, it becomes now the product of I equals 1 to n. You take the f rho times this expression we have here. So this is 1 plus y a rho of g e to the minus f rho over 1 minus a rho of g, of the e minus to the f rho. Everything is in the equivariant cohomology completed of x with rational coefficients, and to fix everything, f rho is of course the equivariant fundamental class of the corresponding divisor. And what you more or less do is you apply the Chern character to this. The Chern character will give you these factors, so that this in K theory becomes this in cohomology is easy. But the problem is to put all things together. That one has to guess. But we really have a very explicit global formula for the Hirzebruch class. And maybe in the talk of Richard tomorrow, he will lecture about fundamental classes and deformed with a parameter. So what we are doing here with the Hirzebruch class is the deformed, the parameter is y. And the deformed version is of the fundamental class in K theory. So it would be the structure sheaf, and we take more sheaves into account. So if you plug into this formula y equals 0, you get the formula for the Todd class of a toric variety going back to Brion-Verne. So that is the deformation formula with parameter of what Brion-Verne has done many years ago already. And the ideas, of course, go all back to them. The beauty is that the machinery works completely with this deformation parameter if you put things together. So now, via localization by this linear algebra with geometric series, we have a global formula for the Hirzebruch class. Can we use it for something? And of course, now I come to the last piece I want to explain. Now I want to come to what is Euler-Maclaurin formula. Maybe you have never seen about what it is. So now I want to explain this application. And it's good to have, or for this, if you want to make this application explicit, it's good to have an explicit description of these Hirzebruch classes. I will explain the result in full generality for any coherent sheaf. Of course, then it does not see anymore the polytope, then it only sees the character lattice. But if you plug in natural things related to the polytope, it will always be the sum over characters which are in the polytope and some ratings and so on. But I want to say that you can do this for any coherent sheaf, and that this is in principle a translation of equivariant Hirzebruch-Riemann-Roch. So how is this done? So for sure, from now on, I need P simple for many things. Of course, we used already for Poincare dualities that I work in cohomology. But now I really have to work with the simple, and what we are doing now, we make a small deformation of this polytope. We still take the same inequalities we had before. So the standard presentation I have taken here, and this pairing was of course between the dual lattices, I didn't mention maybe. So with AF, this was the presentation we have taken before, but now I allow to move this a little bit. Yeah? So F a facet, and the corresponding parameter HF small. And the good thing is, simple is a kind of transversality condition, so if you make a small movement, it's still simple. But it's not a lattice polytope anymore. It's a simple polytope. So this is still simple. Later on, maybe I want to do the same for a face. So if I take a face E, of course, I get this deformation of the corresponding face E. And we take now h small, so that this is very simple. What are the final players I need? I still need, let's see. So the pairing, we extend now from the real lattice on one side, but on the other side we can even allow complex parameters if you want. This goes now to C. And here is where we take the parameters from. Is that correct? No, let's see. No, on the other side. I want exactly to do the opposite. So M is where my lattices are, and these are in this real vector space, and here I want to work with the real vector space where the polytope is. But now I pair with coefficients, and the coefficients I want to allow even to be complex. So here now, for the dual lattice, I can even use complex coefficients, and here is the parameter z coming from. So we pair with this to get functions. Okay, and the final piece we need is, we have this divisor corresponding to this dilated polytope. T equivalent fundamental class, which you should take as a definition, is just the original one, dp t, and then you take linear combinations h, rho, and now I switch maybe between phases and rho, and please forgive me, I switch between both languages, and you should learn a facet corresponds to array, corresponds to a torus divisor, and here it's now the corresponding divisor class, d rho equivalent fundamental class. Of course, I allow now h are small real parameters, so that would be a cohomology class with real coefficients now, and so on. Okay, so now we have the basic ingredients, and now I can't resist to write the key technical formula. This is not where we want to go, but this is the key technical formula where all the applications are coming from. You integrate now the function e to the mz dm either over this dilated polytope, or there are two versions, or over the dilated face. Both is possible. And we calculate this via localization at the fixed point. So this is an integral of analysis. The backpass is usually normalized so that a lattice cube has volume 1. Because I have a lattice structure, I can normalize the back measure. And this you can calculate now by fixed point contribution. So what you get? Downstairs is clear, there is this Euler factor at this fixed point. Everything gets paired with z. Here you get, to have a quick notation, you restrict to this fixed point this shifted divisor, which we have written here. This is maybe a little bit easier to write, of the shifted polytope, the corresponding real fundamental class paired with z. Sorry, everything fine? And now you get two factors, and I like to write this in one formula because it saves me a few minutes. So if you do this on the full polytope, this is always everything. And if you do this on the face, you get the multiplicity of this sigma e of the corresponding cone times the class of the normal bond you would expect, pulling back the products of these f rows in E1. So that spans the normal bundle, everything paired with this variable z. So this factor in cohomological terms is just making the global fundamental class the fundamental class of the subvariety. And the magic of these formulas, here are really integrals from analysis. Here, this is cohomological language. And what is the idea to prove this? You first take the H rational, you multiply with big powers of a number so that everything gets integer valued, then you are back with a lattice polytope. You apply the equivalent Hirzebruch-Riemann-Roch, and then you let k go into infinity, and these lattice points counting converges as Riemann sums to this integral. Because of course an algebraic geometer can't calculate integrals from analysis, but we can calculate the Riemann sum approximation. That is behind this. And the ideas goes partially back to Brion-Byrne. We do this in general. And the nice thing on these formulas, here everything is cohomological calculation at the fixed points. And here is the hard integral from analysis. So for example, you see here, of course, it depends continuously on h. A priori I needed h rational, now I can take hq. Here you see it becomes a meromorphic function. So maybe you have some poles here, but because it's continuous, in the end everything is analytic in the parameters h for small h. So this is a beautiful formula I would like to give first, because that is the key for proving things, and this is a converter, the machine, converting integrals into cohomological language. And now I give the final application, how the Euler-Maclaurin formulas are looking like. And then I've done my job for today, and we all can drink a lot of wine. So let's see, what is now the beautiful theorem, which I think in this generality is completely new. Of course, part of this, or very special examples people have done before, but the point we want to sell is one can do this for any equivalent coherent sheaf on the toric variety. And it's a translation of localized Hirzebruch-Riemann-Roch. So what we get now? Now comes the Euler-Maclaurin formula. And I have two of them. So what I fix? I fix the coherent sheaf T equivalent on my toric variety. And the thing is, we apply differential operators to these kind of integrals or something. And the magic is, where are these differential operators coming from? And these are infinite order differential operators. They come from power series. And the magic is, or what people know is, they come from the Riemann-Roch, they come from the Todd class. So what I'm doing is, I'm taking now presentations of the Todd class of the sheaf. Assume that I would know a presentation of this, and we have two versions. So the first version would be, assume I have an explicit expression in terms of the fundamental classes of the divisors in what we call the equivalent cohomology ring analytic inside the completed equivalent cohomology ring. Because what you have here is you have a Steiner-Weisner presentation of this. So this is a quotient algebra of just a Q in the formal power series in the F rows. And what we mean by analytic means you can choose a representative which is a convergent power series. So here we would like to have that this P of the F rows is really sitting in, I don't know if this is a standard notation, coming from a convergent power series. Because the problem is these are infinite order differential operators, and we have in the integral we have an exponential. So it goes up. And P is this, I take a power series in these variables. This projects down to the equivalent cohomology, and I assume that the Todd class has such a presentation. So for example, for the motivic Chern class, that was the explicit formula I've given you. So for the motivic Chern class, you take this formula and read this as a power series in the variables, and it's a convergent power series. So you can take this formula. And we can show that any Todd class has such an analytic representative. And the analytic is needed if I work with the exponential. I have a second formula where you start to represent this as coefficients Pi in some variables Ti times the equivalent fundamental classes of orbit closures. That is always possible, but we cannot make it very explicit. But theoretically this is possible. And here these coefficients, they of course coming now, Ti, they come from Q formal power series in the Ti, which in the end was the completed symmetric algebra of M. And here maybe you go to MQ, which you can identify by the sign we have chosen with the equivalent cohomology of a point. So what we are doing here, Here we in principle only use the Q structure of the equant cohomology ring. Here we are using the module structure over the cohomology of a point, and that gives me some other power series and a basis chosen. And using either this or this, we can produce now two formulas, and then I'm finishing. Give me just this 1 minute. So what is now the theorem? Or maybe I put it here. What is now the big theorem? So now comes the big theorem. F, a polynomial function on MR. And now we can calculate. We go to this deformed integral over this deformed lattice polytope. We want to integrate not just the exponential but also this function e to the mz. To this deformed integral we apply an infinite differential operator, which is just differentiating as these deformation parameters and then evaluate at h equals 0. And this p, which we choose, is the power series representing the Todd class. Or, in the second formula, we get the sum over all faces of the polytope. We get an integral over this face, no dilation anymore. We differentiate with the other parameters, with the p, ei, in the direction on the ambient vector space, just on f, and take this integral and sum this up over the faces. So, and the thing is, this uses the Stanley-Weisner ring description. This uses the model structure over the equant cohomology of a point. These come from the Todd class of the Courant sheaf. And what both integrals are calculating, this is the same. They calculate Hirzebruch-Riemann-Roch. So what is coming out? You get the sum over all lattice points. You get now this Eckler and Euler characteristic of H star x OD tensor F at this eigenspace. And here now is coming dependent on which you do this. Here we can allow f of m times EMZ. Here we can do this with an exponential, or in the other version we only can do this for polynomials. So you get the sum of these functions evaluated on the lattice points, either polynomials or either multiplied with exponentials, and the prefactor you plug in are these coming from the equant Hirzebruch-Riemann-Roch. And if you use natural coefficients, you get expressions of functions over lattice points in polytopes. Here I should stop.
So, are there any questions?
Here's the wine.
So, this is, you assume that this is for smooth toric varieties?
No, that's the point. For smooth, everything gets much simpler, and you have not to make this game with the characters. So the formula you get for the label class is just you would think about that the ways are Chern roots of your tangent bond, which is not true. You have more boundary divisors than you have the rank of the boundary. But the formula is, in the smooth case, stays the power series with Hirzebruch introduced, which calculates the Hirzebruch class, and plug in for each boundary divisor the corresponding fundamental class. That would be the formula in the smooth. What makes the orbifold so more difficult is you get these fixed point contributions.
Yes, but so if you suppose it's not orbifold.
If no orbifold, the same formula works, and of course they look much, much simpler.
No, I mean really singular.
If you go to really singular, this method does not apply because we are coming from the deformation picture, from the first version. And for the deformation, we need simple so that the nearby is still simple, and that is used. And from the deformation, we go where these two formulas are presented. We go from the one formula to the other in the end. So there are Euler-Maclaurin formulas for any toric by Pommersheim, Brion-Byrne, but they use completely different techniques. And at the moment, it's not clear if this can be so smoothly generalized to any coherent sheaf. They use something like birational invariance, and that does not work for any coherent sheaf. So there we have to do something which is not clear. This is restricted to simple in this generality.
Any other questions? Okay, well, let's close the session. Thank the speaker again.